All the presenters, you should upload your presentation before the beginning of the session, please.
The microphone?
It will be, I think they didn't start the session yet, but it will be fine, you don't have to touch anything.
Une par mail qui est arrivée là il y a 2 minutes.
Ah ok, très bien. Pour cette saison?
Ouais,
Sorry, I just interrupted. À Colt?
Test. Oh. Très bien. Il est parti où? Qui? À la réagir? Ah, sorry.
Let's see. It works, right?
Can try.
Hello, hello. Yes. Okay, so we'll start the session. Nathalie Bruchin is going to talk of dice and games, a theory of generalized boosting.
Hi. Thanks. Yeah, I'll talk about a theory of generalized boosting. And this is joint work with Marco Bressan, Niccolo Cesabianchi, Emmanuel Esposito, Ishai Mansour, Shai Moran, and Max Thiessen. So we're talking about a classification problem where we're given a bunch of classified data points, and the goal is to correctly classify a new example. And formally, this is the classic PAC learning framework, where I'm thinking of a classification problem as a joint distribution over the domain X and the label space, where in this case the label space is 0, 1, but as I'll mention towards the end of the talk, our results apply more generally to the multi-class setting as well. But for now, think of binary labels. A learning algorithm gets as an input m training points from the distribution and needs to output a classifier with the goal of having a low error with respect to the distribution, where the error here is a simple classification 0, 0, 1 loss. And we typically assume that the distribution is realizable with respect to some known function class, which means that the infimum of the error with respect to the class is 0. Okay, so, and we say that a PAC learner for the class is an algorithm that for any realizable distribution, when given enough training points, it returns a classifier that has low error with high probability. Okay, so what if we don't have access to this strong PAC learner? So this is where boosting comes into the picture, and we have this beautiful classic result by Freund and Shapiri from '95 that tells us that it's enough to have a weak learner with an error that is just slightly better than random guessing. So as long as the error is less than a half, is half minus gamma for some positive gamma, there's a boosting algorithm that can improve the error, push the error arbitrarily close to 0. So we have a partitioning of the error space to a random guess region. Above half, we will get it by random guessing, and below it, we can boost it arbitrarily close to 0. So that's great, but this does not apply for general losses. And in this work, we're generalizing boosting theory beyond the simple 0-1 loss. And also, the classic theory does not generalize as well to the multi-class setting. And in this work, we give a unified framework for general loss functions for both binary and multi-class classification. So what do I mean by general loss functions? So we're thinking of cases where different types of mistakes have different costs. So as a motivating example, think of diagnosing a sick person as healthy, which is the false negative error, could be far worse than diagnosing a healthy person as sick, which is the false positive error. And in general, we define a cost-sensitive loss matrix, in which we give different values for the different types of mistakes. In general, if we have k labels, we have a k by k matrix, where making the mistake of predicting label I, when the true label is j, has a different cost. So that is the matrix, cost matrix W. And for a given matrix W, we define the loss in the natural way. We take the expectation over the distribution, where the mistakes are weighted by the cost matrix. And even more generally, we consider multi-objective loss functions, where we have a sequence of these matrices. Each correspond to a different criteria that we want to satisfy. And for each one, we have a different loss value. So loss value for W1, W2, and so on. So we have a vector of loss values, which we want to track simultaneously. So now we can define the multi-objective learning for a given sequence of cost matrices and a point Z, which is the learning guarantee we want to reach. Z is a point in 0, 1 to the R. And we define a WZ learner as a natural generalization of PAC, such that for any realizable distribution, when given enough training points, for each one of the R coordinates, we want that the ith error would be bounded by Zi. So as an example, if we just have one criteria, R equals 1, you have the symmetric cost, and Z equals 0, this just recovers PAC learning. If I replace Z by half minus gamma, this recovers the classic notion of weak learning. But we can have more interesting types of learners, like the false positive, false negative errors, when I have two coordinates, each tracking one the false positive and one the false negative. And in general, the boosting question that we ask here is, can we boost a WZ learner to a W0 learner? So that's the general boosting question that we ask here. Okay, so just to focus on a simple example, consider the false positive, false negative case, where I have a point Z in 0, 1 squared representing the two types of errors. And I have a learning guarantee here in this plane, and I'm asking when can I push that arbitrarily close to 0, or asking differently, which points can I attain by random guessing? So maybe it's easy to see that if the sum of the points is above 1, so this upper triangle, this can be attainable by flipping a biased coin. So this is the red region is attainable by just random guessing and therefore cannot be boosted. What happens below this, this region, so the lower triangle? Can it all be boosted? Is it attainable by random guessing or some other third option? So that's the question to keep in mind. The way we address this is by taking a game theoretic view of random guessing. We define a two-player game over the label space, with the minimizer being the predictor and maximizing being the environment, and we think of the cost matrices as the payoffs. When there's a single cost matrix, this is a zero-sum game with the game value defined in a natural way, the maximin of the expected payoffs. Where there's multiple objectives, so this is more complicated, it's no longer a zero-sum game, but we define a coin-attainable region, we denote this by C of W, essentially all of the points that are attainable by flipping a random coin. Okay, so our main results for the binary case are, first, the single objective case, a WZ learner is boostable if and only if Z is below the value of the game. And in the multi-objective case, if and only if Z is not in the coin-attainable region. So essentially, we get a dichotomy. We have that a learner is either fully boostable or it's attainable by random guessing. And we have an efficient boosting algorithm with polynomial sample size and runtime for both of these cases. In addition, for the false positive, false negative case, we also have a nice geometric description for this coin-attainable region. So completing the picture that we saw before, we have this nice curve below which everything is boostable, above which everything is attainable by random guessing. So in general, we generalize the phenomena of this dichotomy. What we have as a boostability threshold of half in the symmetric one-dimensional case. Now in the multi-objective case, we have that the boostability threshold is actually a curve. What happens in the multi-class case, so when I have more than just two labels, I have K labels, so I don't have time to tell you about that, but we have a lot of results for that case as well. I'll just tell you in general that the story is more complicated here. Rather than a dichotomy, we have a multichotomy. So we have a partitioning of the space of attainable learning guarantees into a finite number of regions, where for each region, if I have a learning guarantee in this region, I can boost it to any point on the Pareto frontier of that region, but provably not beyond it. As an example, in the single objective case, I have a partitioning of the range between 0 and 1 into different buckets, and I can boost within each bucket to the lower end of this bucket, but not beyond it. So we get a landscape of the boostability thresholds, both in the binary and multi-class settings for generalized multi-objective loss functions in the high-dimensional case. We have a complete characterization of the weak learning guarantees, which can be boosted and to which point. And also, let me say that in the binary and cost-sensitive multi-class cases, we also have efficient algorithms. In the multi-class, multi-objective case, which is the most general one, efficiency is still an open question. And I encourage you to read the paper, and happy to talk about it more offline. Thanks.
I guess the boostable set is an open set, and as you approach the boundary, things get worse and worse. Can you say something about that in general? Or?
So, for example, in this image, so I can reach any point on the boundary.
So the boostable region includes the boundary?
So in either case that I'm in, for example, with a biased coin, I can get biased coins that just sit on the boundary, on the Pareto frontier on the boundary.
Right. I was asking about the previous result about false positive, false negative. You have a boundary, and presumably the boostable set in that case is an open set, and as you approach the boundary where you can achieve things randomly,
So for example, in the false positive, false negative case, which is this image,
okay.
The blue region is the boostable region, and I can push arbitrarily close to 0. So I can reach the point 0.
I see, but I'm asking, is the blue region an open set?
No.
Then in the regular boosting case, binary classification with equal losses, it certainly is. You have to have the margin strictly.
So okay, maybe the definition is the difference, because I'm defining when I'm approaching a point here is attainable if I can approach it.
I see.
Yeah, that's the difference.
Thank you.
Any other question? If anyone has, you can ask. Okay, let's see. Yes.
In the multi-class case that you have there, does the attainable, the volume of the attainable region as the number of classes increases, does it go to 0, or how does it behave?
That's a good question. It depends on the structure of the cost matrix. Yeah, but if you have a symmetric cost, for example, so all the costs are symmetric, you get these kind of regions where they go arbitrarily close to 0. Yeah.
Thank you.
The next speaker can come. If anyone else has a question, you can ask in the meantime. Okay, so Michael is going to talk about improved margin generalization bounds for voting classifiers.
Hello, everybody. So this is joint work together with my advisor, Kasper Gren Larsen, and it's titled Improved Margin Generalization Bound for Voting Classifiers. So we will start with the setup, which is binary classification. So we have some learner, which is giving a number of samples in, where x is some input space and y is -1, 1. And we assume that each of these examples are ID from some unknown distribution, and we can just think of this example where we get pictures of apples, and the label is whether the apples on the picture is good or bad. The goal of the learner is now to make good predictions on new pictures of apples drawn from the same distribution over the input space. And the solution is that the learner produces some predictor which is a mapping from our input space into -1 and 1. So this could, for instance, be this predictor, which on this input outputs good. However, it's not clear that we just want one predictor. Maybe we would have multiple predictors, and now we would come up with some way of aggregating their answers, and that could, for instance, be assigning each of these predictor a weight, and then we would predict good if the sum of the predictors saying good is larger than that of the bad weights, and vice versa. Right? And this is exactly the idea about voting classifiers. We have some hypotheses class H of VC dimension D, and then we define the class of voting classifiers as the sum of every possible linear combination of classifiers in H, where these weights are positive and sum to 1. And then when we want to make a prediction, we take the sign of f for some f in this class of voting classifiers. Good. And having set up in this way, we have a nice interpretation of the prediction on a new point. Namely, we can split it into the sum of the classifiers which predicts 1, and then their weights, minus the sum of the weights of the classifiers predicting -1. And then we get some interpretation of f of x as some sign certainty score of the label. So if we had that f of x is close to 1, then we say that the prediction is more certain. If it's around 0, it's uncertain. And if it's -1, it's very certain it's -1. Right? And now we can take this step further. So for a point x, y, we will define the margin. That's the product between the label and the prediction f of x. And we can again split into the sum of the weights of the classifiers predicting y minus the sum of the weights of the classifiers predicting -y. And again, we get some nice interpretation, and it's basically assigned accuracy. So if the margin is 1, then the sum of the weights predicting y is 1, so it's very certain of the correct label. If it's close to 0, it guesses somewhat uncertain. And if it's a -1, it makes a large mistake because it's predicting the opposite label. Good. Using this, we can then define the margin loss for some example x, y, and that is the indicator function of the margin be less than gamma. And we can also make that clear in the picture over here. So we would plot gamma on the y-axis, and then the green dotted area, that's where the margin loss is 0, and the red striped area, that's where the margin loss is 1. Okay. And we can also define this for distribution, so it's just the expectation over this indicator function. Good. And it was then shown in some early experiments that some boosting algorithms obtained good margin, and to the end of saying something about generalization, it was studied how the margin of a classifier led to generalization. So now we'll talk about some previous works. And all these bounds are, say that with probability 1 minus delta over the sample, it holds for all if in the convex combination that the 0-1 loss, the classification losses, is upper bounded by some quantity. And the first case we will be looking at is work by Schäfer, Freund, Bartlett, Lee, which also introduced this idea about margins and generalization bounds. And they showed that the classification error of f is upper bounded by the empirical margin loss, gamma margin loss, plus some square root log h, log m, gamma squared over m. This was then followed up by work by Breimann showing that if the gamma margin loss empirically was 0, then you could also get this fast rate, so you could remove the square root. So you kind of see that we have this two cases. We have this agnostic rate with the square root, and then we have the realizable, gamma realizable rate. And it was then shown by Gao and Zhao in 2013 that you could nicely interpolate between these two cases. Namely, they showed that the classification error of f is upper bounded by the gamma margin loss of f plus some square root, the gamma margin loss empirically, d, which is now the VC dimension, log m over d log m over gamma squared over m, and then the same factor without the margin loss in the square root. Good, and this is the bound we improve over. And to explain our bound, we need to define this gamma function, which is log of x, log x squared. So we show the generalization bound, which is that the classification loss of f is upper bounded by the gamma margin loss plus the square root, the gamma margin loss of f, the VC dimension multiplied by this gamma m gamma squared over d divided by gamma squared over m, and then the same factor without the square root and the margin loss. So we notice that this is an improvement of a log squared factor. But for our application, the important part is actually inside these log factors, we now have a m gamma squared over d instead of this m over d and log m, which is smaller. Good. And so which implications do this bound have? So we know that adder boost, introduced by Schäfer and Freund, when given access to a gamma weak learner, which is something which output a hypothesis given a distribution which is slightly better than guessing, obtain a gamma margin loss of 0. So just plugging into the new bound, we get that a generalization bound of adder boost of O d gamma over m gamma squared over d over gamma squared over m. And this is off by a factor log m gamma squared over d squared from a lower bound of adder boost. So it's closer to getting a tight generalization bound of adder boost. And now where this m gamma squared over d factor was important, again, we have adder boost, and then we show that if you take the majority vote of 3 adder boosts, then you get an optimal weak to strong learner in expectation. And this improves over work by Larsen Mathiasen from 2014, which showed that the majority of 5 adder boosts also obtained this bound. And in the proof, it is, at least for us, crucial that this m gamma squared over d factor shows up in the log. Good. And this also shows that there's no kind of, for these majority of x bounds, there's no inherent difference between the realizable case where Aiden Ali showed that a majority of 3 also obtained this bound in the realizable case, so without the gamma squared factor. Good. And that's it. Thank you.
Any questions? Can you give us something about the proof of your theorem?
Yes.
And the next speaker can already come.
Yes. So the proof reduces to kind of this 2-step. There's this discretization step, where you actually kind of meet in the middle. So you start with the 0 gamma margin loss, and then you relate it to the gamma margin loss of the classifier by going into the empirical gamma loss at gamma halves. And then kind of compared to previous bounds, we use a covering by Vachine and Rudelson, which kind of gives this improvement. And we also do some clipping of the classifiers, because just intuitively, when you want to show generalization for margin classifiers, you don't really care about the behavior outside of the range of gamma. And it might seem a bit niche, but kind of clipping this classifier allows us to actually get this gamma squared inside the bound here instead of just gamma. And that was key for our application.
And so what do you mean exactly by interpolating between 2 classifiers?
Yeah, I think I was not talking about interpolation. I was just trying to, at least if it was this let me just, if it was this slide. Yeah, I was just talking about here we have like, if you think of normal classification, then this looks like the agnostic case, you have the square root, and this is kind of realizable, right? You assume that there is some classifier obtaining 0 gamma margin loss. And then this bound here, if you set the gamma margin loss to 0, right, you recover the fast rate. You recover without the square root. This term is, right, if this is 0, this is 0, this is 0. So you get like 1 over m, more or less, instead of square root 1 over m.
Okay. I think, Michael, a question?
Yeah. Your final bounds are in expectation.
These are high probability. The generalization bound is high probability. The last one is in expectation.
Okay. Can you get the last one in high probability as well?
That would incur some log factors, log, most likely. Yeah.
Thanks.
Thank you.
Okay, let's thank Michael. Okay, Manuel is going to talk about are all models wrong, fundamental limits in distribution-free empirical model falsification.
Right, thank you, yes. So exactly this is what I'm going to talk about, and this is joint work with Yuchen Liu and Rina Fadil-Baba, both of whom are at the University of Chicago. And the setup we're considering is a very standard one. So we have curly Z, some data space, curly F, some family of functions, and then L, some loss that takes a function in our family of functions in our model class and takes a point in our data space and assigns it some non-negative loss. And the setting you should really have in your mind during the whole of this presentation is a regression setting where curly Z would be the product of some covariate domain and a response domain. Curly F could be given by the family of all linear functions or a smoothness class or a family of functions indexed by some neural network architecture or anything like that. And the loss could just be the squared loss. And then we define the risk under P of F as the expected loss incurred by the function F if we sample our data point Z at random from the distribution P on curly Z. And then finally, we define the model class risk as the smallest you can make this risk over your family of functions, over your model class. And so this is a quantity you've all seen many times before, also in the past talks. And hopefully now I show you a question that you haven't thought so much about before, namely, given an IID dataset, Dn, sampled from a distribution P, can we conduct meaningful inference on the model class risk without making any assumptions on the distribution P? And to make this more precise, what we're after is lower bounding the model class risk, which is a bit unusual maybe. So what we want is a function L hat alpha that you feed into your sample, and then you get a distribution-free lower bound on the model class risk in the sense that for all distributions P, the infimum is over all distributions, we're not making any assumptions. The probability that L hat alpha is less or equal to the model class risk is at least 1 minus alpha. And just to note, we could also be asking how to upper bound the model class risk, but that's an easier problem because the model class risk is defined as an infimum. And so to upper bound it, you just need to upper bound the risk of any specific instance in your model class, whereas we need to lower bound the risk of all functions in our model class at once. So there is an asymmetry here. But if you can do both of these tasks in a distribution-free manner, then what you achieve is that you can get a distribution-free upper bound on the excess risk. So this is one of the motivations for this project. Okay. Now, so this is the task we have, and there is a very trivial solution to it. You just take L hat alpha, you allow randomization, and take it equal to 0 because the loss is non-negative with probability 1 minus alpha, and set it equal to, say, infinity with probability alpha. And the only issue is that the only informative, so non-zero value that the loss can take will be attained with probability at most alpha. And so we're going to call all distribution-free lower bounds that have this property of being positive with probability at most alpha and maybe some vanishing term, we're going to call those trivial because they don't really tell us much. And so the question is, can we even get non-trivial lower bounds? Okay, here I first have some good news, and then some bad news will follow in a bit. So as for the good news, so a natural starting point would be to look at the empirical risk as defined in the first quantity here, and then also look at the empirical model class risk, so the smallest we can make the training error, kind of the optimized training error over our model class. And of course, this optimization problem can be arbitrarily difficult. We don't care about this in this talk. We only, let's just assume we have access to this optimized training error. Then one thing that we could do is we could construct a distribution-free lower bound in the following way, as given here. And validity of this approach follows just from Markov's inequality, and since this is a session on concentration inequality, I should highlight that if the loss is bounded or we use some truncation argument, we can improve this bound to something that as n increases, converges to this optimized training error. Okay, so this is all well and good, but the issue is that this lower bound is going to be positive if and only if your optimized training error is positive. But in many modern settings of interpolation learning and so on, where we choose curly f, your model class, to be very large, you will often have the case that the optimized training error is actually equal to 0. And so the question is, can we still get a non-zero lower bound on the model class risk in those cases, or do we just have to be like, okay, so if the optimized training error is 0, then we actually can't have any evidence against the model class risk, the test error, the best possible test error over our model class, to also just be 0. Okay, and this is where some bad news come in. So with respect to this question, there is indeed a fundamental hardness. There is an upper bound as to how large we can make lower bounds on the model class risk, which is telling us that with high probability, any distribution-free lower bound on the model class risk can at most be as large as the optimized training error over capital N many data points, an extended sample that now has capital N rather than small n many data points in it. And so to make this a little bit more approachable, consider a setting where curly f and p are such that we can even interpolate, if you think about the regression setting, capital N many data points where capital N grows more than quadratically in small n, then any distribution-free lower bound must be trivial. So this is kind of the fundamental hardness that we have. Okay, so to summarize what I've shown you so far, and to pin down some of these interpolation notions I've been mentioning, let's define two notions of interpolation capacity. The first one gives us the largest possible data set size, such that we can almost surely optimize to 0 training error. And the second one, a larger quantity, gives us the largest possible data set size, so that we have a chance of observing optimized training error equal to 0. And then what I've shown you essentially so far is that there is a low complexity regime where we can't interpolate n many data points, and hence the optimized training error over small n many data points is going to be positive. And so we can have a distribution-free lower bound on a model class risk that's also positive, just by the construction I've shown you 3 slides ago. And then there is a high complexity regime where the interpolation capacity is greater than n squared. And in that case, by the fundamental hardness result on the previous slide, no distribution-free lower bound can be non-trivial for those cases of curly f and p. And so there is a bit of a jump from the interpolation capacity being less than n to the interpolation capacity being larger than n squared. And the question is, which of these bounds is loose, if any of them even is loose? Okay, so what about the gap? So it turns out that this gap is inherent, and it's not just something that we are kind of missing in our proofs or anything like that. And so to illustrate why this is the case, let's first look on the left side, where we have this n here. And let's look at a very simple example, namely that of linear regression, where the covariate domain has d dimensions, and we take the squared loss. And then in cases where P has a density on your data space, we have that the interpolation capacity notions are both equal to D. And then we have, now in specific cases where P has, again, a density, and the covariate distribution is multivariate normal, we have, in all cases where D grows faster than N, and so D is equal to the interpolation capacity here. So if the interpolation capacity grows faster than N, we have that any distribution-free lower bound must be trivial. And this is like for the specific case where the covariate distribution is normal, but in the paper we have far more general results. So this is actually something that holds over a much larger class of distributions, that any distribution-free lower bound will be trivial in those cases. So this is showing how this bound at n is kind of tight. And then so regarding the bound n squared, if you look at the case of piecewise constant regression, and throughout we're not talking about like fitting really anything, we're just talking about like class of functions that we're allowing for. So this could be the result of random forest or some other tree-based algorithm where we end up with piecewise constant functions. And so if we look at the class of piecewise constant functions parameterized by m, which gives us the number of distinct values, the number of partitions of the functions in that class we allow for, then there exists actually a choice of m that depends on n in such a way that it grows proportionally to n squared, such that the following here gives a distribution-free lower bound on this class of piecewise constant functions. And note here that on the right-hand side of this definition, we have the optimized training error over a smaller functional class, namely that with only n-1 constant pieces. And so in, again, a case where P has a density, we have that the interpolation capacity of this family of functions is going to be n squared. But at the same time, we have that almost surely the optimized training error is going to be positive because we can't use n-1 constant pieces in order to interpolate n many data points. And so this means that the lower bound is going to be positive, and hence shows the case in which we can have a non-trivial lower bound while at the same time having interpolation capacity proportional to n squared, showing how the bound at n squared is tight. And so to summarize our findings, so the question we posed was, when can we construct empirical non-zero distribution-free lower bounds on the model class risk? And this is actually driven by two phase transitions in terms of the interpolation capacity of our family of functions, where in the low complexity regime, all is well, and we can just use concentration inequalities. Then there is an in-between regime where it really depends in a more fine-grained manner on curly f and p. And then in the high complexity regime, where your family of functions is so large that it can interpolate more than n squared many points, no non-trivial lower bound on the model class risk can exist. And with that, thank you all, and thank you to the organizers.
Any questions? Yeah.
Very nice. I'm actually curious, where, do you have some examples of applications where we want to have this lower bound? On the
Right, yeah, that's an excellent question. So the main motivation was what I mentioned here in the beginning, right? That you could then combine like an upper bound on one specific function in your function class, or on the risk of it, and the lower bound on the model class risk in order to, in the end, get distribution-free upper bounds on the excess risk. But also more generally, the idea is that in some cases you might want to know, when you look at how you choose your family of functions, how you choose your model class, and you want to determine is your learned rule performing poorly just because you have a large estimation error and you just need to collect more data, or is it actually due to the approximation error and you really kind of need to increase your function class?
I see. Okay, thanks.
Okay, let's thank Manuel and. Okay, so Nati will talk about quantifying overfitting along a regularization path for two-part code MDL in supervised classification.
Okay, thanks. And This is work by Xuan Zhu, who unfortunately couldn't be here because of visa issues, so I'm presenting, I mean, it's joint work, but she should really be the one presenting this, and I'm presenting mostly on her behalf. Okay, so I'll be talking about, this is a mouthful, the two-part code MDL in supervised classification. So supervised classification, hopefully you're all familiar with. Let me just tell you what I mean by the two-part code MDL. So this is the following learning rule. So you have some prior pi. I just said that word, but I mean, we're never assuming anything comes from that pi. So just think of it as a distribution pi specifying your prior belief or your description language, if you wish. And we choose hypothesis minimizing this combination of the first term, which is the prior, and the second term, which relates to the error of the classifier. And you can interpret it either as a minimum description length learning rule, where you can think of like you're thinking of the looking for the minimal description of your labels. So you're first describing the predictor h, and the first term is the number of bits you need to describe the predictor h using a coding based on the prior pi. And the second term is the number of bits you need to describe the labels in the way they differ from your predictor h. Or you can also think of this as just a map estimate based on the prior pi. So if you have like a model where your labels are generated by h with the Bernoulli noise, and you're taking a map estimate over the level of the noise on h, you get the same learning rule. So this is a very natural learning rule motivated by either, again, this Bayesian or MDL perspective, which are in some sense equivalent. So this is great. The only problem is learning rule is actually not good. So already in 2004, Peter Greenwald and John Langford observed that this learning rule can be inconsistent, which means that even if there exists some hypothesis H star, which actually has very high prior, and I have the number of data points goes to infinity, right? So even if I have the limit of infinite data, the limiting error can actually be worse than the error of the true error for H star. So I can't actually learn. I don't get like agnostic pack learning or maybe more contemporary language. The behavior is not benign in some sense, right? We don't actually approach a limiting error, and this is. Disappointing, since there definitely are rules here, very simple rules that are consistent. So the simple approach here would be to take a structural risk minimization or bound minimization approach, which amounts to this learning rule. Learning rule is not so important. The important thing is this does actually give us consistency. So whenever there is a hypothesis with positive prior, the limit of infinite data, and even with the amount of data just scales proportionate to the description length under this prior, we do actually get good generalization. We get a limiting error, which is at least as good as our reference predictor H star. So let's try to, again, understand what's going on here. So both of these predictors are actually very similar. Both of them are minimizing some combination of the prior and the error of this prior. And in fact, this is actually what we do in many ways in machine learning, kind of all the time. We always want to optimize some balance of data fit, or the empirical error of H, and simplicity, or like description length, or prior here, negative log prior of H. So we want to find a predictor that's both has good fit and is simple or is good under this prior. So we're really solving this bicriterion optimization problem. I would argue this bicriterion optimization problem really is the way to think about pretty much all of learning. So what's the difference in these predictors? They're both selecting Pareto optimal points for this bicriterion optimization problem, but different Pareto optimal points. And maybe the easiest way to see it is if instead of this two-part code MDL, we move to the modified two-part code MDL, but just weighing the first term, this prior term, by lambda. So the standard MDL corresponds to a choice of lambda equals 1. And the SRM approach, if you kind of see what is the relative scaling of the error and the negative log prior, it roughly corresponds to selecting lambda, which is square root of m. Okay? And so in some sense, what's going on here is that the correct amount of regularization is square root of m, and the standard MDL or map estimate is severely under-regularizing. Okay? So it's in some sense overfitting. Now, it's not overfitting all the way. It's not interpolating. Okay, that would correspond to lambda that's a 0 or goes to 0, but it's still under-regularizing comparative to the kind of what the SRM approach tells us is the right amount of regularization, which is square root of m. Okay, okay, so so I think we can view this in our maybe contemporary understanding in terms of the effect of overfitting and under-regularization. And what we see here, we can interpret Grunwald and Langford's result is saying that the overfitting here is not benign. Right? The overfitting here does have a cost. We actually do not recover the optimal rate. But now we can ask, just how non-benign is it? Is it catastrophic? Is it really bad? Is it only slightly worse? Okay, so I think best we can view it this way. So what we're showing here is the limiting error. Okay? On the y-axis is the function of the reference error, the error of h star. Right? So that's what the error we want to compete with. So the SRM approach gets this green line, which is the optimal thing you can hope for. Right? So when the number of samples goes to infinity, we always are guaranteed to have error which is not worse than the optimal error. So this is just the line y equals x. Okay? And when lambda equals to 0, we can actually get, for some priors, we can get catastrophic behavior here, which means the error would be really bad. And what Grunwald and Langford showed is they gave a lower bound on the error for this MDL predictor, which is given by the blue line. So there's only a lower bound, so that means that the actual error might be anywhere between this blue line or all the way up, so the entire blue region. Okay? And they didn't actually succeed in getting an upper bound. They gave an upper bound to a different predictor, which is not exactly the same, which is given by this line, but even this line still leaves a lot of gap. Okay, so what are the contributions here? So the first thing we do is we resolve this question, and for the standard two-part MDL code with lambda equals 1, we give the exact worst case rate, and this is given by this simple function here. And I think instead of looking at the function, it's better to look at the plot. On the left, this is this brownish line. I apologize for people who might not see the colors that great. This is this brownish line, and that is an improvement. I mean, it's in some sense improvement over the lower bound. We see the real behavior is actually a bit worse than the lower bound they gave. But what's more important is we also show this is the exact worst case behavior. So this is also an upper bound. So we characterize the exact worst case behavior for lambda equals 1. But let's go beyond lambda equals 1. So we already know that when lambda goes to 0, the behavior can be really catastrophic. I mean, there are some priors in which we'd get catastrophic behavior. But what happens in between? Okay? So we can actually get the behavior for any value of lambda. So first of all, for lambdas between 0 and 1, we get the simple function in the exact curves we're seeing here. And as we see that as soon as lambda is less than 1, strictly less than 1, okay, so let's actually, maybe go back to lambda. Let's stick to lambda equals 1, which is the brown line. For lambda equals 1, the behavior is tempered in the sense that as long as your reference error is strictly less than half, then at least you're going to get weak learning in the sense that the error of the two-part code MDL would also be strictly less than half. Okay, so as long as you're at least getting something. Okay, you're never as bad as random guessing. So the random guessing here is the line at 0.5. As soon as lambda is less than 1, okay, then you get this partially tempered behavior. So if your true error is very small, then in fact you get tempered behavior, but this crosses this line at some point, so you do not get tempered behavior all the way. Okay? On the other hand, once lambda is bigger than 1, then we can again establish the formula here is a bit more complicated. If you're really interested in it, I suggested looking at the paper. But we get an explicit form, and we get these curves that become closer and closer and closer to this optimal benign or consistent line of y equals x. And in fact, as soon as lambda goes to infinity, we don't have it to be exactly square root of m. As soon as lambda goes to infinity, we get consistent behavior. Okay? And just to complete the picture, this is true as lambda goes to infinity, but not too quickly. If lambda goes to infinity too quickly, like it's really huge, we get underfitting, right? And again, we can be catastrophic. Okay? So what we see here is a complete characterization of the overfitting and underfitting behavior, or under-regularization, over-regularization, using a generic prior. Okay, so why should you care about this? Well, first of all, it resolves this question from 2004 and extends it, but really, this learning rule is the generic template learning rule. Many learning rules can be seen as special cases of it. And our analysis here is a worst case analysis. So this shows you the worst case overfitting behavior for any possible prior. Okay? Now, specific priors can, of course, be much, much better, have much better overfitting behavior. And in fact, we have some examples of such priors. And in some sense, this analysis gives you the baseline. And any type of overfitting analysis should be measured relative to these curves. Okay, so let me end here and again remind you that this is work by Xuan Zhu, a student in statistics at the University of Chicago, and I'll be happy to take any questions.
Any questions? Yes.
Yes, Tim.
So it seems that in your asymptotic analysis, the influence of the prior drops out, right? You don't see the difference anymore between different priors, but I guess that would be a big motivation for working with general priors.
Okay, so let me separate that for the answer to two steps, or three. First of all, this is worst case for all priors. And so there's some priors. Of course, you can have like very degenerate priors. If the prior is entirely concentrated in a single hypothesis, then you'd always be perfect because you'd always choose that hypothesis, and that's the only hypothesis you allow. But there are other priors also that can have much better behavior. For example, Kolmogorov prior has much better behavior for this. This is something we showed 2 years ago. So again, this is, I'm not sure if that was exactly your question, but again, this is kind of a baseline for all priors. The second thing is that what I'm hiding here, and maybe so different priors really are mostly different in what value they assign to different hypotheses. So this analysis assumes that there exists some hypothesis with positive prior. Okay? And I think this is. Can you see this? No, you can't see this. So this is in the super. We require that it assigns some prior, and this is an asymptotic analysis. How fast you approach it would depend on the level of that prior. So in all of these results, in order to get this asymptotic regime, the number of samples has to scale as negative log prior of H star. So if you choose, if we choose different priors over the same set of hypotheses, we might have the same behavior, but we'll get there in very different times. The sample complexity would be different. Does that answer the question? Or?
So do you also have, there's something about finite sample rates on the slide. So do you have that in the paper?
Yeah, I didn't write it on the slide, but all of these are written asymptotically here. But in the paper, we give finite sample upper bounds that show you exact. So basically show this for each of these regimes, the term here plus another term that's where everything is explicit in finite sample in with the sample complexity that has a term of the form like negative log pi over m, and then other terms that just depend on lambda and L star.
Thanks.
Okay.
Any other question? Okay, let's thank Nati and that's it.
Yeah, so the first plenary talk is in 6 minutes here, and so there's a very short break before Francis.